In this video, we're going to go through a brief introduction to other galaxies beyond our own Milky Way galaxy. So this is a pretty phenomenal image that was taken in the mid-1990s. Hubble Space Telescope pointed its lens at a dark spot of sky. Literally, astronomers picked a spot of sky devoid of any stars, just black, and said, let's see what we can see. Well, we saw a lot more than we ever realized. We saw billions and billions of galaxies everywhere. So this image, called the Hubble Deep Field, taken in 1996, is really one of the first indications that we really aren't alone out there in terms of our galaxy. There are billions of other galaxies out there. And in this lecture, we're going to take a look at the few of the types of galaxies that we see pretty consistently across the universe. Okay, so if you had to classify galaxies, how would you do it? Would you pick color or size or shape or something else to classify galaxies? Take a look at all these different galaxies in this image and think about how would you classify these galaxies? A pretty common response is by using size and shape. And this is how Edwin Hubble first classified galaxies, and is really the primary way that we still classify galaxies to this day. So Edwin Hubble really had two major contributions to astronomy that we're going to talk about in this course. First is the discovery of galaxies and the classifications of galaxies that we're going to talk about this lecture. And the next lecture we'll talk about his contributions to cosmology and our understanding of the expansion of the universe. So first, Hubble discovered the universe has billions of galaxies, okay? We were able to confirm this by a lot of our images like Hubble Space Telescope and spectroscopic observations. And so Hubble really was into the world of cosmology, which is the study of the universe, how it formed and how it is today, and how it will end. Literally the study of the universe as a whole. So Hubble classified galaxies to begin with based on their appearance. So he labeled galaxies as spirals, S, barred spirals, SB, ellipticals, E, and irregulars, IRR. So let's take a look at these four broad categories, okay? So he identified spiral, elliptical, and irregular in those barred spiral. I'd say there's four broad categories. Add in there active galaxies, and we'll talk about what those mean. Okay, spiral galaxies, something like our Milky Way. So those arched lanes of stars, just like you've seen in the last pictures we talked about with the Milky Way galaxy. So those spiral arms contain hot, young, blue, population 1 stars, and hydrogen regions where lots of star formation is taking place. They also contain some kind of central bulge, this yellow-red color bulge in the center that contain both old and newer stars, but mainly population 2 stars, where we don't see a lot of star formation happening. Notice that spiral galaxies can be further classified in terms of A, B, and C, mainly distinguishing between how the arms look and the size of the central bulge. So notice that an SA type spiral has smooth, broad spiral arms with a fat central bulge, whereas an SC contains narrow, well-defined spiral arms and a tiny central bulge. This is just a way to further delineate the spiral galaxies. Okay, barred spiral. This is an indication of the essential shape of the bulge. So you still have the spiral arm structure, but this time it originates at the end of a bar-shaped region in the center of the galaxy, where that central bulge has this elongated shape. So we've, under more recent observations, have concluded that our Milky Way galaxy is most likely has more of a barred spiral shape to it. So just like the spiral galaxies, barred spiral galaxies can be further delineated into A, B, and C, based primarily, again, on how those spiral arms look, as well as the central bulge, with A having the large central bulge and C having the tiny central bulge, comparatively. Okay, the next type of galaxy are elliptical galaxies. These look pretty much like they sound. They're elliptical in shape, okay, no spiral arms. Generally, it looks kind of just like the central bulge, okay? So elliptical galaxies are further classified by number, E0 through E7, where an E0 elliptical galaxy is more round, and an E7 galaxy is flatter. Okay, down in the image below is an E6 galaxy. So elliptical galaxies are pretty unique, okay? One of the main unique things about them is they are devoid of interstellar gas and dust, meaning that they don't have a lot of interstellar gas and dust. Instead, they are made up of old population 2 stars with small amounts of metals. So these are like old, red, and dead galaxies, okay? We see two main types of elliptical galaxies. We see large giant ellipticals and dwarf ellipticals. These giant elliptical galaxies aren't very common, but they are huge, whereas dwarf elliptical galaxies, shown in the lower right-hand image, are much more popular. Okay, so if a galaxy doesn't really fit into spiral galaxies or elliptical galaxies, we call them irregular galaxies. These galaxies are rich in interstellar gas and dust. They have both old and young stars, but mainly young stars where a lot of star formation is taking place. Two really good examples of irregular galaxies are the large and small Magellanic Clouds in the southern hemisphere. So if you're from the southern hemisphere, these are probably pretty familiar to you in your night sky. Whereas if you're from the northern hemisphere, you probably have never even heard of these. But the large and small Magellanic Cloud are two really distinguishing cloudy-looking features in the southern sky. But they're not clouds at all. In fact, they are galaxies. These are regular type galaxies. Just like the other types of galaxies, we can further delineate irregular galaxies in terms of type 1 and type 2. Type 1 have some kind of hint of an organized structure, and you see a lot of O and B type stars in the heavily regions of H2, so lots of star formation. Irregular type 2 are more asymmetrical and distorted in shape. Primarily, we believe, caused by collisions with other galaxies or other kind of violent activity within the nuclei. So I just said galaxy collisions. So we think that galaxies do collide with one another. This especially forms in nearby clusters within a group of galaxies. So the result of a galaxy collision, of course, as you can imagine, is that interstellar gas and dust is stripped apart, then smashed together, where new star formation can begin. Okay, so emergence of galaxies can be pretty interesting and possibly form these irregular type galaxies. So Hubble devised what he calls the Hubble tuning fork diagram to outline stellar evolution. Notice we have elliptical galaxies on the left, then moving on to our spirals, and then our irregular galaxy. Now there's one more type of galaxy I didn't talk about here, which is the lenticular galaxies. These galaxies are an intermediate between an elliptical and a spiral galaxy. They're considering that they're probably somewhere in the middle in terms of morphological classification. So they contain large-scale disks and a bulge. They don't have discrete spiral arms. Okay, they're consisting of mainly older population 2 stars, but they're in that weird mix where they have the bulge, but not very clear spiral arms. So again, they sit here in between the ellipticals and the spirals in Hubble's tuning fork diagram. So notice that his classification of galaxies is purely based on the size and shape characteristics of galaxies. So which type of galaxy, as review, has the oldest stellar population? All right, hopefully you answered those elliptical galaxies, those ones that are devoid of interstellar gas and dust, containing those old, red, and dead stars. Now, the fourth type of galaxy I brought up was active galaxies. These are also often called quasars because they look like stars because they emit large amounts of energy. What's also neat about quasars is they have a large redshift. Therefore, they're very far away, and they're in fact the farthest away objects we've ever really seen. So in a sense, it's looking back at time. So these quasars are the oldest objects that we've ever observed in the universe. They were formed when the universe was very young. So active galaxies are believed to originate from a black hole at the center of a galaxy. So this is an image of a quasar, okay, this galaxy with a very bright center to it, so quasi-stellar object, okay. They emit large ranges between the radio and the X-ray, so lots of energy coming out of these, okay, lots of radiation. But it's more than just starlight, okay, it's a galaxy with a black hole at the center. So here's a question for you. Do galaxies exist independently, or are they parts of groups of galaxies? What do you think? No, they don't exist independently. In fact, galaxies are parts of groups. Okay, galaxies aren't scattered randomly throughout the universe. They exist in groups. So we have poor clusters and rich clusters and superclusters. Poor clusters are like our local group of galaxies. There's also richer clusters like the nearby Virgo cluster, which contain lots of galaxies, where our local group doesn't really have too many galaxies in it. Okay, so here's an image of our local group, okay, kind of in a disk plane. So Andromeda, of course, is within our local group of galaxies. Superclusters are clusters of galaxies that are further grouped, okay? So local supercluster is the local group and the Virgo cluster plus others. That's our local supercluster. And in the next lecture series, we're going to talk about how these galaxies, we have these clusters of galaxies and then spaces of just nothing in the universe and then more clumps of galaxies, which is pretty cool.